Today we will discuss key concepts in communication under Module 4, which includes amplitude modulation, angle modulation, and radio digital modulation. Here is the table of contents of today. Our group member is Dan Wing Yi, Lim Junning, Lo Shia, and Siti Noor Amira. Let's dive into how these modulation techniques work and they are important in modern communication. To start, let's define modulation. Modulation is the process of varying a carrier signal to transmit information. Why is this important? Because it enables efficient transmission of signals over long distance, which is the foundation of all modern communication systems. Now, let's focus on amplitude modulation. It varies the amplitude of a high-frequency carrier wave in proportion to the message signal. This creates sidebands that carry the information. AM has several variants based on how the carrier and sidebands are transmitted. Number one, we have double sideband full carrier. Both sidebands and the full carriers are transmitted. Double sideband suppressed carrier. Both sidebands are transmitted, but the carrier is suppressed to save power. Single sideband, only one sideband is transmitted. Single sideband suppressed carrier, similar to SSB, but with the carrier removed. And the last one, vestigial sideband, transmits only one sideband and a partial version of the other. Let's begin with double sideband full carrier. So this is the input signal that contains the information to be transmitted. And for the carrier signal, a high-frequency sine wave that acts as the base signal for modulation. It does not carry any information initially, but enables the transmission of the modulated signal over long distance. So this circuit that combines the modulating signal with the carrier signal will produce the AM modulated signal. So here is the equation of resulting signal after modulation. The modulated signal in the SBFC can be expressed like this, and here the EC is the carrier amplitude, the FC is the carrier frequency, and the MT is the normalized message signal. So the spectrum of the SBFC signal consists of the carrier frequency component FSC and two sidebands located at FC plus FM, which is the upper frequency, and the lower frequency. The modulation index M quantifies the amplitude variation relative to the carrier, where EM is the maximum amplitude of the message signal and EC is the carrier amplitude. So depending on M, for M equal to 1, the carrier's amplitude matches the message signal, creating a clear waveform. And for M less than 1, the envelope doesn't fully modulate the carrier. And for M larger than 1, the envelope intersects, distorting the signal. The total power in a DSP-FC signal is the sum of carrier power PC and the sideband power PSB. So here is the formula, and the R is the load resistance. And from that, we can get the total modulated power. From the total modulated power, we can calculate the transmission efficiency. The efficiency is the ratio of sideband power to the total power. So this shows that the efficiency increases with M, but over-modulation reduces signal creativity. Generation of the SBFC. In the direct method, the carrier and the message signal are directly combined to produce a modulated signal. So here is the mathematical expression. This approach is simple but less efficient for higher frequency carriers. The indirect method involves a two-step process, carrier separation and carrier insertion. So number one, the message modulates the carrier without the carrier being transmitted, and then the suppressed carrier is reintroduced at the transmission state. So this method is more efficient for high-frequency signals, and here is the figure illustrating the indirect generation process. Next, we discuss the double sideband suppressed carrier, DSP-SC. The DSP-SC modulation has a mathematical expression derived from its process of modulating a carrier signal without transmitting the carrier itself using trigonometry identity.
The spectrum of SSB-SC includes only one sideband, the upper sideband USB, which contains FC plus FM, or the lower sideband LSB, which contains FC minus FM. This efficiently halves the bandwidth compared to the DSP.
The total power in a DSB-SC signal is purely due to the sidebands, where EM is the message signal amplitude and the R is the load resistance. Since there is no carrier power, DSB-SC has higher transmission efficiency than DSB-FC, typically close to 100%. In the direct method, the carrier signal is modulated by the message signal, and the carrier is suppressed using a balanced modulator. So here is the mathematical expression. Balanced modulator ensure the carrier components is cancelled. The indirect method involves two steps, carrier modulation and carrier separation. So they modulate the carrier with the message signal and then use filter to eliminate the carrier, leaving only the sidebands. So here is the typical block diagram of the SBSC generation. Next, let's explore single sideband suppressed carrier SSB-SC. So the modulated signal for SSB-SC can be represented as here, and in SSB-SC only one sideband is retained, significantly reducing the bandwidth requirement compared to the SBFC and the SBSC. As you can see, the spectrum of SSB-SC includes only one sideband, the upper sideband USB and the lower sideband LSB. So this effectively halves the bandwidth compared to DSP. So we would say that the modulation index for SSB-SC is similar to the SB-SC, however, the carrier amplitude is suppressed and not transmitted. And for the power of SSB-SC, the power is so concentrated entirely in a single transmitter sideband. Since only one sideband is transmitted and the carrier is suppressed, SSB-SC achieved the highest achievement among the AM techniques. In the direct method, the carrier is modulated and one sideband is filtered out. So filters are used to remove the unwanted sideband and the carrier. So the indirect method, also known as the phasing method, generates SBSC in two steps. Number one, generate the SBSC, modulate the carrier signal with the message signal, and next, sideband selection, use phase shifting networks to cancel one sideband, leaving only the desired one. And this method requires persist filtering or phase adjustment to avoid distortion. And here is the typical block diagram includes a modulator, phase shifters, and sideband filters. Finally, let's look at the vesicle sideband VSB. So the partial retention of one sideband helps preserve low-frequency components of the message signal while reducing bandwidth requirements. In the direct method, the carrier is modulated and a selective filter is used to retain one full sideband and the vesicle portion of other sideband. And the indirect method involves modulation, creates a standard AM signal, and filtering use phase filters to remove part of one sideband while retaining a vesicle for the others.
Angle modulation, introduced by Edwin H. Armstrong in 1931. Unlike amplitude modulation, which focuses on varying signal strength, angle modulation uses a modulating signal to vary the frequency and phase of a carrier signal. The general sinusoidal signal expression allows us to either modify the amplitude or the angle of the carrier to convey information. This modulation is crucial for improving signal quality and resistance to noise, ensuring better quality communication. A quick comparison: amplitude modulation involves changes in amplitude of the carrier wave, making it more susceptible to noise since amplitude is easily distorted. Angle modulation, on the other hand, modify the frequency or the phase of the carrier. These fundamental differences makes angle modulation more resilient to noise and interference. This makes angle modulation ideal for clearer, more reliable communication. There are two main types of angle modulation. First, frequency modulation (FM). The carrier's frequency deviation is proportional to the modulating signal. Second is the phase modulation (PM). The carrier's phase deviation is proportional to the modulating signal. Interestingly, FM and PM share a close relationship. For instances, FM signal can be generated using PM modulators and vice versa. Other than that, it's because frequency is the rate of change of phase and phase is the integral of the frequency over time. To generate FM using PM modulator, pass the modulating signal through an integrator to convert frequency variation into phase changes. To generate PM using an FM modulator, pass the modulating signal through a differentiator to convert phase variation into frequency deviation. This relationship adds flexibility in system design. For example, FM signal can be demodulated using PM demodulator by first passing the signal through a differentiator and vice versa. On generation of FM signal, there are two primary techniques for generating FM signals. First is the direct methods. These include varactor diodes, reactance modulation, and voltage control oscillators. These modify the frequency directly. Second is the indirect method. The Armstrong method is a popular example of indirect generation, where FM is generated by first creating a PM signal and then integrating it. FM has two main types based on the modulation index. First, narrowband FM, NBFM. Modulation index is less than 0.25. The bandwidth is equal to 2 FM. It is commonly used in mobile communication where smaller bandwidth is sufficient. On the other hand, is wideband FM, WBFM. The modulation index is more than 10. The bandwidth calculated using Carson's rule, BW equal to 2 bracket beta plus 1 bracket FM. Ideal for broadcasting and entertainment due to higher fidelity and wider range. The key difference is that WBFM uses more bandwidth to achieve better sound quality, while NBFM is compact and efficient for limited spectrum application. Now, moving on to radio digital modulation, where digital signal are used to modulate an analog carrier. The three primary techniques are amplitude shift keying (ASK), which switches the carrier amplitude between high and low state, representing binary 1 and 0. Second one, frequency shift keying (FSK), involved in generating and summing two ASK waveforms with different frequency. Third, phase shift keying (PSK), modify the carrier's phase based on the digital signal, typically between 0 degree and 180 degree depending on the binary input. On amplitude shift keying (ASK), ASK changes the carrier's amplitude based on the digital input, high for 1 and low or 0 for 0, simple and widely known as on-off keying. On frequency shift keying, FSK uses two carrier frequency for 1 and 0. It's made by combining two ASK signal with a summing amplifier. On phase shift keying (PSK), shift the carrier space, typically 0° for 1 and 180° for 0, offering noise resistance and reliability in digital communication.
Communication technologies have drastically evolved in recent years, shaping how we connect, work, and live. One groundbreaking advancement is massive MIMO, multiple input and multiple output, which is transforming wireless communication. So this massive MIMO uses multiple antennas to serve many users simultaneously, improving data rate and efficiency. So the recent advancement includes AI-optimized antenna configurations, hybrid beamforming for cost-effective performance, and energy-effective designs like antenna that harvest energy from radio wave. Massive MIMO improve connectivity in rural areas, enabling technologies like smart city and IoT. It drives economic growth by supporting industrial like telemedicine and automation while reducing network costs. Environmentally, its energy efficiency makes it a sustainable choice for communication network. Concerns about health and radiation exposure are addressed by focus beams, which reduce RF energy compared to traditional systems. Advanced spectrum management prevents interference, and culturally tailored platforms support local traditions while connecting communities globally. In the future, Massive MIMO will support 6G technologies, autonomous systems, and immersive XR experience, revolutionizing connectivity and ensuring real-time communication in various industries. In summary, Massive MIMO enhances connectivity, supports sustainable growth, and addresses misconceptions, making it a cornerstone of future communication. Thank you.